So in order to find tau, we need to draw it at time greater than 0. And remember, the real challenge with finding tau is finding REQ. What resistance does that capacitor see? And it's not really obvious, is it, when you look at how op-amps work. For time greater than 0, we're not in DC steady state, so we cannot replace the op-amp with a open. We can replace VS, though, with something simpler. What's VS?
Can you replace it with a 6-volt source?
Right. That U of T came on, so this is just a constant 6 volts. And so already, you know, if it's 6 volts relative to ground at that node, it's going to be 6 volts relative to ground up here. That's all good stuff. Now, of course, there can be a current flowing through RA, so it's not going to be 0 volts across RA. So here's something brand new. When finding REQ, you know, meaning since tau equals REQ times C, you need to find REQ. For op-amps, I want you to do 2 things. The first is 0 all your sources in your circuit, and the second is replace. When you want to 0 all your sources, of course. Whenever you're finding tau, you 0 your sources. But now you've got this dependent source, which is this op-amp, and you got to kick it into action somehow. So you're going to replace your capacitor with a test source. And just trust me, this test source you want to use is a I test of 1 amp. And then the V test is going to be across your I test, and that will tell you what your REQ is. By Ohm's law, it's just whatever your V test over your I test is. And now that you know your REQ, now you can find your tau, which is equal to that REQ times your capacitance. So this is a separate call out that's true only for op-amps. Well, it's actually true for everything, right? I'm just describing what the rule is to find REQs for op-amps, but it works for anything with dependent sources. So let's do that. I'm going to redraw this with our test current. I think that's everything.
Sir?
Shoot.
Would that current be flowing the other way because of how we drew it in the first diagram?
Ah, that's a neat idea. So you're saying that because up here, don't we have to draw currents in this direction?
Yeah.
The answer is no, because this current is a test current. It's not related to this voltage. Here's where we need to draw it. Here's where we need to draw things in certain ways. If we define a current through this capacitor, and we want to use the rule I equals C dV dt, then we have to define our current I sub C in that direction. Okay?
Okay.
But our test current we can draw in any direction we want to, and we'll get the same answer no matter where we draw it, in what direction. I like your idea, though, about being careful about where we're drawing these currents and do they impact with any voltages. Someone else have a question?
Yes, sir, I did. I was going to ask if you could explain that one more time. I just wasn't following.
Sure. The question is, does the direction we draw our test current, is that influenced by the direction in which we defined our V sub C? And the answer is no, because V sub C is independent of our test current. The things that we have to worry about our direction of V sub C is that if we define an I sub C such that we want to use the constitutive relationship for a capacitor, that's the only time that we need to worry about V sub C and I sub C. For this I test, all we need to be careful about is how we define our V test. And we have to define it coming out of the more positive terminal in order to have our I test work. The fact that we drew our V test in the opposite direction of our VC doesn't matter because they're different thought experiments. Is that clear?
Right.
If it's not clear, then by all means draw your, if it's not clear, by all means draw your test current going in this direction, draw your V test in this direction, and drive on. But you don't need to, because this thought experiment is different than this. I mean, for instance, this is 1 amp. IC is definitely not 1 amp. So it's just it's almost like a different problem we're analyzing. And there's nothing secret about the way that I did it to the right. I just chose this direction totally and completely arbitrarily. In fact, if anything, I chose it a little bit just to be different than the way I defined I sub C and VC on purpose, to show you that they're different values, that this 1 amp is not the same as I sub C. Shall we drive on?
Yes, sir.
So our first thing is to zero our sources. So I should have zeroed this. Let's zero our source. And now we want to find V sub VT. When I look at this, I kind of see the same sort of problem that we just did. I want to do a KVL around this loop. I want to do the KVL around this loop because I want something that picks up this V sub T. And if I do a KCL, I'm going to be measuring currents, but I'm not going to pick up the V sub T. So that I want something that involves V sub T. And so I have to go through it. And then when I go through it, I could go through to the right, but that looks more complicated. This looks really simple because, in fact, I know some of these voltages already. What's this voltage going to be?
0.
0. I mean, maybe, and again, I drew it a different sign convention. It doesn't matter. It's 0. I just don't know what this voltage is. If I could figure out what that voltage is, the whole problem would break apart, because I could do my KVL. I'd know what this voltage is, plus this minus this unknown voltage, plus 0 equals 0, and it'd be set. But I got to figure out.
Wouldn't it just be 1 amp times RQ?
Yeah, that's exactly it. I do know what this voltage is, and I'm not going to. And is this voltage equal to 1 times RA?
Yes.
Almost, not quite. Look really carefully at the sign convention. Remember, I chose the sign convention kind of randomly here.
It'd be -1.
It's negative. It's negative because here our current enters the more negative and exits more positive. And you know, for a resistor, it has to exit more negative than it entered. So this is actually, this voltage is, I'm going to write it down. KVL would be equal to here's my V sub A. It equals minus VA minus VT plus 0 equals 0. So I just need to figure out what my VA is, but I know my VA is equal to minus 1 times RA. Does everyone see why VA is equal to minus 1 times RA? Anyone need, is it a better way to phrase that is, does anyone want a better explanation about why VA is equal to minus 1 amp times RA. And just to be totally clear about this, if we define our I here, we have to define, if we're going to use Ohm's law, we have to define our voltage, entering more positive and exiting more negative. So therefore, back to our KVL, we get our minus RA minus VT equals 0. And so that means that our VT has got to be equal to our RA. And now that we found our V test, now we can say our REQ has got to be equal to V test over I test, which is equal to RA over 1, which equals RA. And now, with the hard work done, we can say our tau is always equal to REQ times C. And so that's equal to our RA times C. And RA is equal to 20K times 5 micros, which is equal to 100. Let's see, K times a micro is a milli, or that's 1/10. So that was a lot of work, but everything just started to fall apart once we figured out how to find VT, which was that loop. And it was so easy to find because VA is so easy to find because we chose our test to be a test current. And that's why I suggest up here to always use a test current source. Questions on that, on those first 2 steps?
Yes, sir. I have a quick question. How did you find REQ? I'm following up to that point. I'm just not use REQ.
Whenever remember when we're doing Thevenin equivalents, there's 4 ways to find a Thevenin equivalent. And the last way, the hardest way, the one that you want to avoid if you can ever avoid it, is when you've got just dependent sources. And if you've just got dependent sources, you got to put in a test voltage or a test current. And then your REQ is going to be equal to the ratio, just Ohm's law, of V test to I test. And I'm telling you that for op-amps, you're always better off using a test current instead of a test voltage. So you put in your test voltage, you put in your test current up here, and then you measure to find what is the voltage across that test current. You take its ratio, and then that's defined to be your REQ. Thumbs up?
Got it. Thank you.
How did you go from that 100 M to just the 1/10?
Oh, sure. 100 M is just a fancier way of writing 0.1, right?
Okay.
Which is the same thing as writing 1/10. And it's not, and I'm writing it 1/10. Normally I would just keep it 100 M, right? 100 M is 100 M. But it's nice to write it 1/10 because at some point I'm going to be writing T over tau, and instead of writing T over 100 M, which is correct, it's a whole lot easier writing T over 1/10, which is 10T. That's why I'm writing it in that odd way. This is the hardest part we just did, finding tau, because it requires us to use test sources.